Welcome to the Distinguished Lecture Series. I'm Karen Matthews of University Video Communications. Our program is designed to enrich graduate and upper division curricula with academic presentations by top computer scientists from industry. Its speakers and topics were nominated by computer science faculty of more than 50 universities. This presentation is sponsored by the Digital Equipment Corporation Systems Research Center in Palo Alto, California. Butler Lampson, a respected leader in computer science, received his PhD in electrical engineering and computer science from the University of California at Berkeley in 1967. After serving on the Berkeley faculty, he joined Berkeley Computer Corporation and Xerox Palo Alto Research Center before moving to Digital Equipment Corporation in 1984. He's currently corporate consulting engineer at the Systems Research Center. Butler's talk today is a naming service for a worldwide computer network. It's our pleasure to introduce Butler Lampson. Dr. Lampson.
Thank you, Karen. I want to talk today about the design of a name service for a worldwide computing network, or at least a very big network, one that might, in the end, grow to encompass the whole world. So you should be thinking of this in the same terms as the worldwide telephone network that we have now. This work was done by a group of people, Andrew Birrow, Roger Needham, Mike Schroeder, and myself. And the quote here comes to me through Dave Riddell, who worked on the development and initial deployment of a fairly large-scale distributed name service, which was one of the predecessors of this work. You can see that things don't always go smoothly in this game. It seems good to start by explaining a little bit what we might mean by a name service. So first of all, and what the goals of the whole enterprise are. So first of all, it's a name service, not a database. So the intent is that it's going to store a set of names, and for each name, there'll be some properties, i.e. Strings with associated identifiers. So for example, the name Lampson here might have a password property, which is some random string, and a mailboxes property, which is this list. Of course, there isn't any way to stop you from using this as a database, since you can store anything you want in these strings. But we can certainly guarantee that if you do that, it won't perform very well. It will probably break. The second goal is that it should be highly available. The notion is that a name service is something that you want to use as the foundation of a distributed computing system to locate resources, locate people, and in general hold the whole thing together. So if the name service is broken and you've designed it into your system that way, then your entire system will be broken, which is quite unsatisfactory. So high availability is very important. These have traditionally been the goals of name service designs in the past. Two things that were a little bit new about this design. One is that we wanted something that would be able to scale to a global system. So that means you have to worry about the total size of the thing. It's not acceptable, for instance, to have any single place where all the names have to be recorded, because it would be hundreds of millions of names. It wouldn't work. You have to worry about fault isolation, because parts of it are going to break, and you need to be able to shut them off from the entire thing. There mustn't be any single point of failure, which can cause the entire network to go down, or even which can cause failures to propagate from that single point throughout the rest of the system. You have to worry about evolution, because the thing will start small and will have to grow slowly to a large size. And you have to take account of the fact that there won't be any single agency which is trusted by all the people who have names registered in the system. Now, this is quite different from most computer systems that currently exist, where there is typically some sort of central authority which has to be trusted by all of the players. Clear implication of these requirements for scaling is that the system is going to have to be organized hierarchically. That's the only technique that's known that will accommodate these requirements, and we'll see the nature of the hierarchical organization as we go along. And the fourth goal was to have a reasonably precise specification of the thing, so that it would be possible for a large number of clients of the service to rely on what behavior they could expect, and so that the implementers would have a very clear notion of precisely what it is they have to provide. Since if you're going to have a large-scale service, you have to expect that there are going to be lots of independent implementers of the thing, just as, for instance, lots of people build telephone equipment. But everyone has to agree to a certain set of international standards, which have to be written down quite carefully so that the equipment can interoperate. Okay, the system is organized. The specification of the system is organized into two levels. There's the client level, which is which contains all of the knowledge that an ordinary user of the system needs to have. That is, someone who simply wants to look up names and work his way around the directory hierarchy. And then there's the manager level, or the administrator level, where additional information appears which has to do with the internal mechanisms by which the system obtains its high availability, the precise details of where the name information is stored, and so forth. I'm going to start by explaining what goes on at the client level, and then after we've finished with that, I'll go ahead and talk about the manager level in a little bit less detail. It's reasonably important to have this division because you expect that there are going to be lots of clients of the service who don't wish to be concerned about the internal details. Okay, at the client level, a name has two parts. The first part names a directory, so here it is, ANSI DEC circ, and the second part names some value in that directory, Lampson mailboxes. So this is the directory part. This is the top-level name in the directory, and then there may be various properties like mailboxes, password, and so forth. The reason for the separation is that it's the directory tree that grows and changes its structure as the namespace grows or the structure of the namespace changes. So it's reasonably important to have this two-part division, even though in principle you could think of this as just one long name with a slash here instead of the more definite division that I've shown. So let's start by looking at what the nature of the values that are stored in the name service is. Here's a picture of a directory, which I've called SRC. It has two names registered, Lampson and Schroeder, and I haven't given any detail for Schroeder, but for Lampson I've shown password and mailboxes properties, and the password property is this meaningless string, and the mailboxes property is this list of 3 mailboxes. This is the basic data structure that is maintained internally in the service, and essentially any information that you want to store in the name service you have to code into the structure, and the ground rules for doing that are that you put the names as the labels at the top on these top-level arcs. Then you put the properties at the next level. And then if a property has a single value, you put one node here with the value as its label. If the property is a set, you put several nodes. Of course, you could have coded the set just as a string, but then, as you'll see when we look at the mechanism for updating, you wouldn't be able to add and remove elements from the set individually. You could only change it as a whole, which wouldn't be very satisfactory if the set contained dozens or hundreds of elements. Given this structure, it's fairly obvious that you can name any node by simply tracing the path from the root. For example, this node here can be named Lampson mailboxes Rees. The number is a timestamp which indicates when the update which created this node was introduced into the system. There are actually two kinds of updates, one kind that creates nodes and one kind that removes them. When a node has been removed, it appears in the picture with a slash through it, and that's a reflection of the fact that the semantics of the system requires that you remember nodes that have been removed for a certain length of time, as well as it's not acceptable to simply remove the node. As soon as the delete operation comes in, you have to remember for a while that that node was removed, and we'll see in a bit why that is. So this is the internal data structure. You simply have a tree, nodes with timestamps in them, and possibly absent flags and strings labeling the arcs. Now let's look at how updates work. This is a slightly simplified version of the picture that you saw before. And here are the updates. Here is a set of updates that might have created this value. So I've indicated that there are create updates and delete updates. Here, for instance, there's an update that says create the property BWL with timestamp 4. Well, you don't see that in the picture here. And the reason is that there is a later update that creates a BWL with timestamp 10. That one wins over the earlier one. So it's only permitted to have one arc with a given name coming out of the root, for that matter coming out of any node. And if there are two with the same name, then the conflict is resolved by picking the one with the bigger timestamp. Furthermore, notice we also have create BWL timestamp 4 and all kinds of other stuff. That was another update that was made to assign a password for BWL. But that was also lost at the time BWL 10 was created. So the entire subtree gets lost at the same time that the winning update here comes in. Here's an update that deleted the node for MDS. The assumption is that previously there were perhaps some other updates that inserted a node for MDS with timestamp 12, but this one actually deleted that node. And then here are updates that insert BWL 10 mail, so that's this node, and then insert the password with its value, and then insert this item then insert this item, and finally, the last update that deleted this item. So this is a possible set of updates that could have created this tree. And the rule for deciding what tree you have after you've processed a set of updates is fairly obvious. A create update inserts one of these guys, and it clobbers the previous one if the previous one was identical but had a smaller timestamp. And a delete update simply puts a bar here indicating that the thing's gone. We'll see in a bit why it's desirable to have this sort of update. Right now, let's just concern ourselves with what the semantics of the updates is. Okay, what I now want to do is build up to giving the actual specification of what the update and lookup semantics of the service are. And in order to do that, I need to talk a bit about what sort of specifications we're going to use. So the model of the computation, for which we're going to write the specification, is the standard model, which says that you have a number of independent processes, each one executing a sequence of atomic actions. And the atomic actions in the various processes can be interleaved arbitrarily, except where some explicit sequencing is introduced by the fact that one action reads a value which another action has written. That's the standard model for concurrent computation. Specification is going to take the form either of invariants, which are predicates that have to hold between every atomic action. As in the middle of an atomic action, the state of the system changes in some arbitrary way. But when the atomic action is complete, you can look again. And as soon as you're allowed to look, the invariant has to hold. So this is a statement that is supposed to always be true of the system. The second kind of specification is a postcondition. That is some predicate which describes either what results a procedure is, a particular call of a procedure returns, or alternatively, what property all states of the system subsequent to the return of the procedure are going to have. It has to be all states because of the fact that in the presence of all this concurrency, it's not very useful to simply specify what property the system has immediately after the procedure returns, because right away something else could happen that would change that property, so you never would be able to make any use of it. So that's the style of specification. This is also a pretty standard way of specifying concurrent systems. An important thing to realize about the specifications is that you don't write them simply in terms of the individual values that are stored in the various machines that are implementing the distributed name service. Instead, typically a specification is written to relate the values that are actually stored in the service with sort of abstract or auxiliary values of auxiliary variables, which don't actually exist in any concrete sense, but are there in order to make it possible to write the specification in a reasonable way. So for example, we're going to have an auxiliary variable which is the current state of one directory or one value in the name service. Because of the fact that the service is distributed and that updates can be made on various machines simultaneously, there's no guarantee that there's any single place that you can go and find that entire state. But the specification is going to be written in terms of that state, and the specification is going to say when you make an update, that state is going to, the state of that variable is going to change, and when you read something, what you get back is going to be determined by the state of that variable in some precise way. So this is a perfectly precise and unambiguous way of writing the specification, even though there isn't actually any variable. There aren't any storage locations in the system which actually contain the value of this variable. Okay, so with that preamble, let's look at how we can write a specification for handling the values and associated updates. The basic idea is that you start by observing that any value like that tree that we were looking at previously can be defined by a sequence of updates applied starting at the empty value. So if you want to have Lampson mailboxes and so forth, first you create Lampson, and then you create Lampson mailboxes, and then you create Lampson mailboxes Infidel, and so forth. And after you've applied that sequence of updates, you're going to get some value, and therefore that sequence completely defines the value. We're going to put some constraints on the particular updates that we use. And the constraints are the following. First of all, the updates, of course, are functions that take one value into another. For example, when I do create Lampson, that takes the empty value into a value that has Lampson. When I then do create mailboxes, that takes the value that has only Lampson into the value that has Lampson and mailboxes. The requirements we're going to put on these functions are the following. First of all, they have to be total. So it works to apply one of these functions no matter what the current value is. So it's not necessary to create Lampson first before creating Lampson mailboxes. You could create Lampson mailboxes even on an empty value. That's the first requirement. We have to make sure that the updates that we actually have satisfy these requirements. Second requirement is they have to be commutative. It doesn't matter what order you apply the updates in. So it's okay to first create Lampson and then delete him, or first delete him and then create him. Either way, you'll get the same result. And that's the reason that the timestamps are there, is to make it possible for the updates to be commutative. Otherwise, if you first created Lampson with a password of X and subsequently changed the password to Y, it wouldn't commute, because if you'd done it in the other order, the end result would have been X. Whereas if you do it in that order, the end result's going to be Y. Again, the role of the timestamps is to impose an ordering on the updates which guarantees that the functions will be commutative, even though you just naively thought of them as reads and writes of a memory. They wouldn't be. And the third requirement is the updates have to be idempotent. That is, if you apply the same update twice, you get the same answer as if you only applied it once. It doesn't make any difference that you create the guy twice or that you delete him twice. If you have a set of updates that have these properties, then something fairly important follows, which is it doesn't make any difference what order the updates were done in. All you need to know is what set of updates was used. So the value is completely defined by the set. It's not necessary to actually know the sequence, which was what we needed at the beginning. Okay, given that, we can now write the spec, the basic spec for value updates, and it's this. When you read a value, you're going to get back the value that's determined by a certain set of updates. And that set is not precisely specified, but there's some constraints on it. And the constraints are the following. You're going to see a set which includes all the updates that were done before some timestamp called last sweep. And then there were other updates that were done since last sweep. You're not guaranteed to see the effects of all of those. In fact, you may see an arbitrary subset of the updates that were done since last sweep. Why this peculiar sounding description of how the thing works? Well, the answer is the system is intended to be distributed, which means that updates can be introduced into it at a variety of different places. You can't give a guarantee, or this system doesn't give any guarantee, that you go around and check all the places where updates might have been introduced when you do a read. Instead, you just read from one copy of the database, which means that since all the updates may not have yet reached that copy, it's not guaranteed that what you see is going to include the effects of all the updates. Why would you want to do things this way? It seems as though it would be much nicer to say when you introduce an update, you're going to carefully go around and update all the copies, and that way you could give a much simpler account of how the thing works. It would work much more like an ordinary memory or an ordinary file system or an ordinary database. The price you pay, however, for having a stronger invariant than this one is that you have to be able to get to all the copies when you do a write. Or if you weaken that, when there are various tricks for weakening that, the price you pay is that you have to look at more than one copy when you do a read. If you're willing to settle for this weaker property, then you can have the nice property that you can both read and update the database, even if you only have one copy accessible. And that seems like a very attractive property for a name service where the primary criterion is high availability, and you're not supposed to be using the thing to store data that has complicated consistency conditions. Okay, so that's the basic idea about the spec for values. It's this non-deterministic result of a read. Now, of course, it wouldn't do for the result of the read to be totally non-deterministic. If that happened, then you might have a perfectly good implementation which could satisfy the spec, which said, no matter what updates have been put in, I'm always going to tell you empty. Well, that would be fairly useless. That's the motivation for this last sweep thing. The notion is that occasionally you can go up to a directory and do what's called a sweep operation on it. And at that point, all the updates will be collected and spread around to all the copies. And after that, there's a guarantee that any read will see all those updates that were in there at the time of the sweep. So the last sweep indicates the time of the last sweep operation. We'll see in a little bit more detail how that goes in a bit, because that whole sweeping operation is something that is really only supposed to be visible to the manager, not to the client. The only thing the client can know is this fact that I've just stated. Okay, so much for values. Now let's look at directories. The basic notion for the directory system is it's quite similar to what you have in a standard file system. You have a pile of directories. Each directory has a unique identifier. All the directories are arranged in a tree, and hence a directory can be named by a full path name in the tree. So here's a typical path name that you might have if the thing had grown to a scale which included a national registry. So you might have ANSI DEC circ as a typical path name. And as in most file systems, for example, the Unix file system, you can have links which allow the traversal of other paths than just the paths down from the root. So for instance, you could say ANSI DEC circ TJW is going to have as its value a link to ANSI IBM TJW. So in that way, I could put into my directory a link over to a directory that associated with another company in the namespace. So we get the following picture, which should be familiar to everyone who has used Unix or any other hierarchical file system. Here's ANSI, here's DEC, and underneath DEC there might be a finance substructure and an SRC substructure and perhaps other things. These arrows indicate the links which connect the directories, and backwards arrows indicate the fact that the tree is actually linked in both directions for reasons that we'll discuss briefly in a bit. Okay, so that's the idea of the directory structure, and the point of the directory structure is it gives you the tools by which the namespace can grow and evolve to meet changing requirements. The notion is that within a single directory you register a fairly small set of names, tens or hundreds of names at most, just as you do in a hierarchical file system. And if you want to grow beyond that size, then you make the thing bigger, not by simply piling more and more names into a single directory, but by making additional directories and organizing them into a tree. So how can one grow the namespace? Well, the basic idea for growth is a simple one. It depends on the standard property of hierarchical names, which is that names with different prefixes don't conflict. So if you have a bunch of names that start out ANSI DEC and a bunch of other names that start out ANSI IBM, you can create names that start ANSI DEC without any consultation with the fellow who's creating names that start ANSI IBM. Exactly the same as in a file system. When you have a root directory, if you write /user/ one user's name /user/ another user's name, you get two separate subdirectories within which the two users can create their files quite independently. Let's consider now what you might do if you had been running the name, if two separate companies, say DEC and IBM, managed to agree that they should both build this sort of namespace. So DEC has built one. It has various subdirectories under it, like the SRC subdirectory. And IBM has built one. It has various subdirectories, like the TJW directory. And then in the DEC world now, it makes perfectly good sense to utter a name like SRC/Birrell. These two worlds are supposed to be thought of as completely independent in this picture on the left. Now suppose that progress is made, people agree on more things, and it becomes possible to establish an ANSI registry, and everybody wants to, all of the previous roots, in particular DEC and IBM in the example, want to register under the ANSI registry so that you can have not two completely separate namespaces that can't communicate with each other, but a single namespace. So now we want to be able to utter names like not just SRC/Birrell, but DEC SRC/Birrell. How are we going to do that? Well, the basic idea is simple enough. You create a new directory called ANSI, and you put the DEC and IBM guys underneath it, as in the picture on the right, and that's simple enough. But there's a few things we need to worry about. In particular, what about a name like SRC/Birrell? If you simply take this name and try to interpret it in this new world, it obviously isn't going to work, because what it says is start at the root, take SRC and look it up in the root. Well, it used to be that the root was DEC, and looking up SRC got you to here. Now the root is ANSI, and looking up SRC gets you nowhere. So that's not very satisfactory at all. If you wanted to make this change, you would have to get everyone to start using a different set of names. And of course, as the system grows larger and larger, that's wildly impractical. So what are we going to do about that? The answer is we make use of the fact that the directories have unique identifiers, and we include at the beginning of every name the unique identifier of the root directory. So here, it's not just SRC/Birrell, but it's number 31 SRC/Birrell, where 31 is the unique identifier of the DEC directory. This at least guarantees that when we come over here and try to look this name up, we'll know that we have a problem, because 31 doesn't agree with 99. That isn't quite good enough, though. We want more than just to know that we have a problem. We'd like looking up this name to continue to work, as opposed to requiring that everyone switch over to using the appropriate new name, which is 99 DEC SRC/Birrell. How are we going to achieve that? Well, the idea is pretty simple. We store in the new root a little table of well-known old roots, which maps the unique identifier of each old root into its proper name in the new world. So the unique identifier 31 is mapped into 99 DEC. The unique identifier 52, which was the identifier for the IBM directory, is mapped into 99 IBM. Now if we walk up to this root and say, I want to look up 31 SRC/Birrell, we can consult this table in the gray, and we'll see that what this really means is this, which is a name that can be looked up quite properly in here. So in this way, you can add to the top of the namespace without disrupting the old names. You might say this isn't so great because you have to store in this gray area all the mappings for all of the old roots, and as the system grows, there are going to be more and more old roots, and that's going to become more and more painful. And I think the proper answer to that is, well, yes, that's true, but you have to look at the pragmatics of the situation. It's not particularly difficult to store thousands or even hundreds of thousands of old roots in a mapping like this. And the consequences of running out of space in one of these mappings and starting to not include all of the roots, of the old roots, is that some old names aren't going to be, it's not going to be possible to look up some old names anymore. Well, that's not totally unreasonable. It's probably not a sensible requirement on this system that if a name was, that if it was possible to look up a name in 1950, that it should still be possible to look it up in 2050. There's some period of time after which it's reasonable to assume that the old names aren't interesting anymore and you convert over to using slightly more recent names. So pragmatically, although in principle it's true that as you add more and more roots to the thing, you might end up with millions or tens of millions of old roots and it wouldn't be practical to keep this table. Pragmatically, it seems relatively unlikely that that would actually happen. So that's the story on growth. Now let's look at something which is a little bit trickier. Suppose we don't want to just grow the namespace, but actually reorganize it. That doesn't look like the right picture. Sorry about that. This is not the right slide. So I'll have to I'll have to talk fairly fast and draw on it a little bit. Suppose that instead of simply wanting to add ANSI on top of DEC IBM, suppose that we have a situation in which we already have got this, and now DEC buys IBM. So that means that we'd like to scratch out this link and put IBM in underneath DEC. So that now, where previously you said ANSI IBM TJW, now you're going to say ANSI DEC IBM TJW. So we're going to put in a new link and write IBM on it. That seems fine, but what about the old link? There are probably a lot of people who aren't aware that this has happened or who have old IBM names stored in their file system hither and yon and would like to go on using the old name. How are we going to accomplish that? Well, the answer is you make use of those links that we had before. You leave an IBM link here in the ANSI directory, and you make its value be 99 DEC IBM. So now, when someone looks up IBM in here, he gets this translation of the old name IBM to this new name, and that sends them around this path so that it still works, even though the namespace has been restructured. This is exactly the same idea that the phone company uses. When you move and someone dials your old phone, you get a message which says, the number you have reached has been changed. The new number is da-da-da. You might say, you might then ask the same sort of question that people ask about the phone system. How long does that message stay in place? That's not a question that the specification can give any answer to. It's an administrative decision how long it's important for the old names to continue working. If you're willing to pay the storage for the link, you can leave the old name in place more or less indefinitely, or at least until you find it necessary to reuse the old name for some other purpose. And that's essentially the story the phone company has. They don't leave the forwarding message in place indefinitely because eventually they need to recycle the phone number. Okay, so that's the story on restructuring. Now let's consider sort of the opposite of restructuring. If you're going to have a large-scale name service, you don't want it to change arbitrarily fast, because if you do, there will just be too much load on all the customers. Essentially, if the namespace is allowed to change as fast as it likes, then it would never be possible to remember the result for any length of time, the result of looking up something in the namespace. You would always have to look again on the off chance that the value might have changed. And that's not terribly appropriate for something that's intended to be the basis of a distributed system and consequently has to have a certain amount of stability to it. If you have too much instability, it's not going to be very practical, and also it's not going to be very efficient to go on working your way through this entire structure, starting from the global root, looking up names over and over again, when you know perfectly well that the global root is not going to change very often. So how can we reflect that formally in the structure of the system? Well, the answer is you introduce on each arc linking directories, you introduce an expiration time. So here we see the familiar ANSI DEC circ picture, and we see that the link from ANSI to DEC, the link that's labeled DEC here, has been given an expiration time 15 September 1987. The link from the DEC directory to the circ directory has been given an expiration time 1 October 1987. So what this means is that if you look up 99 DEC and get the value 31, that's valid at least until the 15th of September. And if you look up 31 circ, that is, if you look up circ in the directory 31, that's valid at least until the 1st of October. And if you do a lookup that involves taking more than one step, then that's going to be valid until the minimum time the earliest time that any of the steps on the path might become invalid. So if you step ANSI, DEC, circ, you took 2 steps, you have to take the minimum of these 2, and this is going to be valid until 15th of September also. So the significance of this is that in order to make this work, you have to make a rule that when you change the structure of the thing, you're not allowed to do that until after the expiration times have expired. As long as you live by that rule, then people who do lookups can save that information until the expiration time has expired. They don't have to do the lookup again until after. If I do this lookup and get the answer 783, I don't have to do it again until after the 15th of September. Now you get to choose you get to make the trade-off between how frequently people have to repeat the lookups and how rapidly the namespace can change its structure simply by deciding how far in the future you put these expiration times. If you want the lookups to be good for a long time, you choose expiration times that are weeks, months, or years in the future. But the price you pay for that is that you can't change the namespace very rapidly. When you do the thing that we saw in the previous slide of restructuring the namespace and leaving a link behind, that's considered to be okay as long as the link itself carries an expiration time that's appropriately far in the future, because you can do the lookup, follow the link, and still get the right answer. Okay, that's the story on directories. Now let's look briefly at what the invariants are from directories from the client's point of view. There are 2 essential properties. One is that the directories actually form a tree, and the tree is rooted in a root directory, and the arcs in that tree are the reverse of those gray backpointer arcs that we saw in the earlier slide. If you recall, there was a picture, this one, in which we saw the black downpointer arcs, which reflect the structure of the tree as you normally think of it, and then these gray backward links, which are supposed to follow exactly along with the downward ones. Well, it's a little bit tricky because when you start adding and removing directories and adding and removing copies of directories, it gets to be fairly tricky to make sure that the thing actually remains as a tree. And it turns out that the way to do that is to take the upward-pointing links as primary, not the downward-pointing ones. And the reason for that is that any structure in which you have exactly one upward-pointing link from each node and you don't have any cycles forms a tree. So that's a much simpler property to maintain, to take the upward links as primary and then derive the downward links from them. So from that, we derive the importance of invariant 2, which is that every downward arc in the tree has a corresponding backward arc which has a longer timeout. And that's because the backward arcs are the ones that are primary, and the downward arcs should be derived from them. So the downward arcs should never have longer timeouts, should never have a longer life than the upward ones. So that's what the clients get to expect about the directory structure, simply that the directories form a tree and that it has this backpointer property. The remaining aspects of the service from the point of view of the clients have to do with security. And this is something that is a fairly interesting topic, but it's not one that I intend to discuss in any detail in this talk. The basic notion for security in the system is that you do protection using a standard access control list scheme where you identify the principals who are permitted to do operations on directories and other parts of the namespace by their names in the name service itself. And then you do authentication of those principals based on encryption. So a principal is authenticated by knowing a key. There are some very interesting questions about how to do authentication successfully in a distributed system like this where there is no central authority that is trusted by everyone. Those would be the subject of an entirely different talk. Okay, let's continue now and look a little bit about at the manager's view of things. In the manager's view, there's not a single directory. There's not a single entity for each directory. Instead, the directory has multiple copies. So here we see, for example, the SRC directory expanded out to show the manager's view of it. And the manager knows that there are actually 3 copies of the SRC directory which are stored on 3 machines which are named alpha, beta, and gamma. And the 3 copies aren't necessarily the same. In fact, in this picture, they're quite different. Lampson appears in all 3. Birrell appears only in this one, in the alpha one and the gamma one. Schroeder appears only in the beta one. This is a reflection of the fact that presumably Schroeder the name Schroeder got introduced in the beta copy and hasn't yet propagated to the other copies. The name Birrell got introduced in one of these alpha or gamma, did get propagated to the other, but hasn't yet made it to beta. The name Needham only got introduced at gamma. Now, the obvious question looking at a picture like this is, how do you ever get these guys back in sync after you've gotten them out of sync like this? And there's two answers to that. The sort of quick and dirty answer is that when you introduce an update, you send the other copies messages indicating what the new update is, and you hope that the messages arrive. So here are two messages in flight in the gray boxes. Here's a message that gamma sent to beta indicating that Needham was inserted with timestamp 11. And here's a message that's, let's say, alpha sent to beta saying that Birrell was inserted with timestamp 12. If both of these messages actually get here, then beta will have all four updates and will be completely up to date. But message delivery is notoriously unreliable. Things can break, links can go down, all kinds of problems can arise. So you can't really count on that as a reliable way of getting things up to date. It would be quite unstable to try to build the system around the notion of totally reliable message delivery. Because basically, if anything goes wrong in the totally reliable message delivery, you have no reasonable way to recover. You need a scheme that's fundamentally more robust, that has the property that even if things start to go wrong, you can go back to some stable point and try again. And the fact that you messed up on the first attempt won't prevent you from succeeding on the second attempt. So the notion for that is one that I alluded to briefly before, which is the idea that periodically you should sweep through all the copies. You should gather up the total set of updates, and then you should feed that back to all the copies. If you do that, then you'll end up with all the directories containing at least the set of updates that had been introduced at the time the thing began. So for instance, here I didn't add any new updates with timestamps bigger than 14, and I assumed that there was a sweep at time 14. So now everybody's got all four updates. And furthermore, everyone has a little 14, which is his last sweep time, which indicates that everybody has been the subject of a sweep that was done at time 14, and that anybody who's got last sweep 14 is going to have all the updates up to time 14. Of course, it might be that new updates were introduced, although you don't see any in the picture, with times bigger than 14. Those might exist at only some of the sites. So now you can see the motivation, if we go back to the previous picture, the motivation for that lookup invariant that we discussed. If you go and look up Needham, for example, which has timestamp 11, and you look him up here, you're going to find him. But if you look him up here in beta, he's not going to be there. And that's legitimate because his timestamp is bigger than beta's last sweep time. So you're not entitled to expect that you're going to see Needham. You might see him or you might not see him, depending on whether this message has or hasn't been delivered. Once the last sweep for beta has gotten up to 14, then if you go and consult beta, you're entitled to expect that you're going to find Needham there. And if you don't, that would be a bug. Okay, a final note on the subject of how to keep these things in sync. If we're going to do these sweeps, we have to have a reliable way of finding all the directories. And the basic notion for doing that is that you link the directories together in a ring. So here it is. Alpha, beta, and gamma are linked together in a ring following the gray pointers. Of course, we also have these down pointers from the deck directory to alpha, beta, and gamma. But it turns out, when you look at the details of what you have to do to the various data structures, when you add and delete directories and when you add and delete copies, it's extremely difficult to keep these down pointers always reflecting precisely the correct membership in the directories as things go on, since you can't read all this stuff simultaneously, because remember, it's all being stored in a distributed fashion on all these different machines. Whereas the ring is the simplest possible data structure that can define a set of directories. So we make a rule that the directories that represent the current state of the database are always going to be linked together in a ring. If we create a new directory, then we'll expand the ring to include a new member. If we remove a directory, then we'll contract the ring and take a member out. What happens if we are not able to remove a member in an orderly fashion? It's possible that some member of the ring, for instance, the gamma directory, will no longer be able to function as part of the system. How could that happen? Well, it could happen because you can no longer communicate with the gamma directory. Perhaps there's a phone line to there which suffers some serious damage. You won't be able to communicate with that directory for a long time. Perhaps the gamma directory resides on a machine which is physically destroyed, so that it really is no longer possible to communicate with it. In those circumstances, you need to be able to retrench and go back to a world in which there are only the alpha and beta directories. And that's what this picture shows. We've taken the gray ring and converted it into a black ring, which only includes alpha and beta. Now, this is a somewhat drastic thing to do, because it's possible that there were updates in the gamma directory that hadn't yet been propagated to alpha or beta. Once we stop recognizing that the gamma directory is part of the ring and say the ring only includes alpha and beta, then those updates are gone. Subsequent sweeps are only going to see alpha and beta because they're the only members of the current ring. Gamma's not going to be involved anymore. So the invariant which says that you're going to see all the updates since last sweep is not, in fact, going to find the updates in gamma. So we better make sure that those updates are no longer considered to be part of the database. Otherwise, our basic lookup invariant is going to be violated. So what happens when you do one of these drastic reconstructions where you are not able to remove gamma in an orderly way but have to force it out of the system? We call that creating a new epoch of the directory. And when you do that, you actually have the potential to lose some updates, namely the ones that were stored on directories that were part of the old world but are no longer part of the new world. Okay, so we can summarize all that as follows. The manager sees the following directory invariants. Well, the first thing he sees is the directory D consists of the set of updates that are stored in some directory in the ring. So that's the definition. That's what relates the contents of all these copies to the abstract specification of what the directory itself is, which doesn't correspond to anything that you can physically see. Furthermore, each copy has at least all the updates before its last sweep time. And at most, it has all the updates that are in D. So that says that everybody's at least as up to date as last sweep, and you're not allowed to just make up updates and throw them in. That would obviously be bad. The second requirement is that there's always at least one complete ring. If you didn't have that, then you wouldn't be able to do the sweeps at all. So that would be quite serious. And the third requirement is that you mustn't have two complete rings that don't intersect. Because if you did that, then one person would be able to attempt a sweep on one of the rings, and the other person could attempt a sweep on the other ring, and they would never know that they weren't communicating with each other. But they would do updates independently, and it wouldn't be the case that the updates would get spread around to everybody. So when you change a ring by introducing a new epoch, you have to make sure that it always intersects with the ring that already existed. And that, in fact, is a requirement that it's not possible for the system to enforce. That's a requirement that the administrators who decide to create new epochs by doing this drastic operation have to take care about. Otherwise, it would be perfectly possible while you were creating this ring for some other administrator to say, the heck with alpha and beta, I'm going to create a ring that consists only of gamma. Then you would have two complete non-intersecting rings, and at that point, all bets would be off. Okay, there's one more story to tell about the way this works, but it's a story that's a little bit too complicated for today's talk. It has to do with the actual way in which the servers themselves are named. The basic notion is that the servers are named in the database itself. So, for example, you might have, here's our familiar story with ANSI, DEC, and circ, and here are servers named ANSI mass, ANSI DEC alpha, ANSI DEC circ beta. It's very appealing to name the servers in the directory system itself, in the name service itself, because that way, when you need to locate a server, you don't need a separate mechanism for doing that. You can simply go to the name service itself and look up the server name, and it will tell you what the server's address is. That would be one of the properties of the server in the database. The trick is you have to make sure that when you do that, you don't get into any infinite loops. For example, suppose that the DEC directory were only stored on these two servers, or were only stored on this server, the one called ANSI DEC alpha. Then when you tried to look up the name of the DEC directory, ANSI DEC alpha, you would discover that you have to be able to look up ANSI DEC in order to look it up, because you can't get to the DEC directory without getting to a server that stores it. If it's only stored here, then you have to be able to get here. But in order to do that, you have to find the DEC directory. But you can't do that because you can't find any server that stores the DEC directory without looking up this name. So essentially, you have to have a rule that says that there are always down pointers in this structure, so that every directory is always stored on some server that has a shorter name. And that way, there's a guarantee that when you do this lookup, there'll always be some place to go that won't require you to go through the directory itself and thus get into an infinite loop. So with that restriction, you can get away with storing the directory in its own, with storing the server names within the directory structure itself, and you can avoid infinite regress. I think that's all I have to say today, and we can go on to questions.
I'm Judith Lemon from University Video Communications. Our faculty questions today are from the University of Washington. Butler, it Is there anything in the design that is predicated on a particular level of technology? In particular, will the design be appropriate when we have gigabit networks and megaflop workstations?
I don't think it would be much affected by such changes in technology. It might be that if things go a lot faster, then you wouldn't need to be quite so careful about not having very large concentrations. With much more powerful machines, it might be reasonable to have a single place where you stored hundreds of thousands of names. But if you really want it to be worldwide, it's still going to have to be distributed. So I think the basic answer is no. It doesn't depend on the level of technology.
Does the name service make the job of providing a yellow pages easier, or is it independent of that consideration?
Well, I think it does make it easier in the sense that, in my view, the proper output of a yellow pages is a name service name. And in that way, the low-level mechanism for very reliably getting you from some sort of human intelligible name into network addresses and other essential properties can be decoupled from the much fuzzier task of providing a yellow pages, which is something that I don't think can be subject to such precise specifications and is likely to shift around quite a bit more over time.
Okay. What are the trade-offs between the proposed cache consistency method using expiration times for invalidation and the more usual approach of viewing the cache as only a hint and detecting invalid cache data upon use?
In this design, it's not really possible to detect invalid cache data upon use because you would have to go and consult all of the directories involved in looking up a name that started at the root. The result would be an enormous cascade of inquiries to the root, which just couldn't be supported by any reasonable implementation. So there's not really any option to having expiration times. The only choice is about how long you make them.
Okay. When you say there are precisely defined non-deterministic lookup semantics, to what does this refer?
Well, I tried to say around the middle of the talk that although I didn't give a predicate written down in symbolic logic, I tried to say fairly carefully what I meant by the non-deterministic semantics, namely that when you do a lookup, you get back an answer which is based on all the updates that were done previous to the last sweep and then some arbitrary subset which isn't specified, the precise contents of which isn't specified, of the updates that were done since the last sweep. And that it's relatively easy to put that statement in completely formal terms.
What were the perceived shortcomings of previous systems that you were addressing?
Well, I think there were two. One was that all the previous systems that I know about don't have a sufficiently robust method for making sure that the multiple copies of the database remain consistent. The previous systems relied upon sending the update information around in messages and tried to be very careful to make sure that none of the messages ever got lost. But you can't really guarantee that, and as a result, typically people have to go in with bit tweezers and fix things up every now and then. The other difference is that I don't think any previous systems really seriously considered questions of scale in the same way that this design is done.
This is a two-part question, Butler. To take advantage of a joined piece of the namespace, systems must change their root to be the new superroot. How is the DI for the new superroot given out, and is this an expensive operation?
Well, I think it depends on how high up the new superroot is. If you decide to conglomerate a name service in the United States with a name service in Europe, then yes, it's going to be quite expensive to put out the DI of the new superroot. But hopefully that only happens once a decade or once a century, so it doesn't seem as though the cost per minute is unreasonable.
Okay. By changing roots to the new superroot, all of a system's old names become unreachable if the old root's DI isn't placed into the superroot. Hence, the superroot must store DIs for everyone that wishes to gain access to the new piece of the namespace. For this arrangement to be scalable, don't you assume that most name services will not be interested in using the new superroot?
Absolutely not. You assume that everyone is going to be interested in using the new superroot, and you depend on the notion that the total number of old roots involved is going to be manageable, i.e. not more than a few thousands or tens of thousands. Then it seems quite reasonable that the new root would be able to keep track of the mapping between the identifiers and the new names of that many old roots. If it turned out to be millions of old roots, you would be in trouble. But I haven't been able to find any scenario for how such a system would evolve that would ever land you with millions of roots that you would want to continue to have access to.
And our final question, one that's less technical. What do you think are the requirements for a good systems research project?
Well, I think that's something that's really quite difficult. On the one hand, you need something that has some intellectual substance. And on the other hand, you need something that you can actually carry out and build a usable system. And on the third hand, I think for a systems project to be really successful, it has to have a serious user community. And all these things are interrelated, of course. It's relatively easy to do something quite simple and make it sufficiently solid that you can acquire users for it. But if you want to do something with greater substance, what you typically find is that it takes a lot of effort to actually build something that is sufficiently robust and fits sufficiently well into the existing environment that you can acquire users. And if you don't acquire users, then you never really get a clear view of whether what you've done is successful. All the systems that I can think of that have acquired user communities have discovered a large part of what's been learned that's been interesting has been the result of actual user experience with it, discovering that a lot of the assumptions that had been made didn't really hold up in practice, or that the thing would evolve in unexpected ways or would be subjected to stresses that hadn't been predicted beforehand. So if you can't get users, you can't really do those things. As a result of that, I think the biggest challenge in doing a successful systems research project is to choose the size of it to be large enough that you can actually do something that is interesting and not just a very minor variation on a previous development, and yet not so large that with the available resources you can't build something that's sufficiently real that people will want to use it, and that indeed that people will use it. And the other difficulty, of course, is actually assuming that you're successful in all that, you still have the problem of actually getting a user community. So I think there's a whole complex of considerations like that which account for the fact that it's extremely difficult to do really successful systems research projects. Okay?
Thank you very much.
You're welcome.
And thank you for joining us today. We invite your comments and questions on this presentation. And if you're viewing this on tape, we've provided postcards tucked under the label of the video cassette case. And we'd like to know your suggestions for future speakers and topics. If you're not watching this on tape, our address is at the end of the tape. Thank you very much.